Balaji. He worked in Singapore and Australia as a technical consultant for about 2 years. In India, he worked as an assistant professor in the Department of Aeronautical Engineering for Hindustan University about 4 years and as an instructional designer for 3 years in India. He has completed dual masters in India and Singapore. In Singapore, he has done his Master of Science in Precision Engineering with specialization additive manufacturing and also Master of Engineering in Aeronautical Engineering. He has published 8 Indian patents in mechanical, aerospace and manufacturing.
Welcome to UGC lecture series on additive manufacturing. Today our discussion is about FDM, that is fused deposition modeling, as well how to optimize it. That is also a topic which we are going to discuss. That is process optimization of fused deposition modeling. That is input pressure, temperature, nozzle diameter, material characteristics, gravity and temperature buildup, and how the future of FDM and what is the FDM in real-time applications and freehand extruder, that is 3-doodler. Process optimization. Particularly this is like you can consider like a research area. Consider to be like harder because most of the modification they tried in FDM because it's, as I said, it's very easier and cheaper to buy or even make. There's not much costlier. Even the input material is also a cheaper one. So they have tried with a number of variants in it. But these are all the areas, particularly these are all the particular processor we can do the modification so that we can attain a better product. I'd like to discuss in a research perspective, particularly for optimization of the FDM machines. Okay, input filament. As I said, what is the problem? I am giving an input like a filament. It is going to have a phase change and then it is going to come out of a extruder nozzle. What are all the problem if there is a change in the input pressure? I am giving a filament of thickness hardly say for example very minimum, say for example less than a centimeter. Once it is entering through it, instead I have a fixed extrusion chamber, right? It is going to give constant temperature input. It doesn't know whether the material thickness is 0.5 mm, it doesn't know, or the material thickness is going to be 0.6 mm, it doesn't know. So it has to be optimized in this such a way the material input itself has to have a proper pressure input. That obviously in turn, as I said, it is going to play with the temperature. Say for example, you know very well 0.5 mm has different melting capability than 0.6 mm of material input. So that's why even the material input itself, material loading itself a special category are in this extrusion method, that is also playing vital role. Can you understand? So here what we can do, it has to be very closely coupled with the input, because based on the input level this is going to give the proper pressured input, or we can say the proper, even you can say the proper strength, or we can give to the extruder head, then only we can expect the optimum required output, right? So what we should do, as we said, even there is a minor change or there may be a twist or buckle or there may be knots or whatever it may be, that will going to change your entire product. Can you got it? So input pressure, even indirectly or directly, it is going to affect your outflow rate, you can say, because this is the one with a desired way. Once it is sent in, it is going to give your extruder output. As we say, there is a small variation in the thickness or in terms of pressure and temperature. If there is a more pressured input, here we need to have more temperature to melt it. Again, if there is a melting, we can have a, what do we say, we can have a same nozzle, but here there is a more amount of input. This will give additional pressure to the nozzle. That time there may be possibilities of clogging. So likewise we need to work with this parameter, particularly only if you are going to change a modification, this extruder system alone is sufficient to get a better output. That is the advantage, you can say, that is a major key area to do modifications in process parameter. Got it? So the temperature, that is a chamber temperature, that as I said, it should be constant, that is ideal always. But is it possible to maintain constant temperature always? because most of the systems we are keeping it in a open atmosphere. Even if it is in a closed chamber, we are not maintaining it as a vacuum or any other. Mostly for this, they are not using even any constant atmosphere, say for example argon or krypton or whatever it may be, because the material doesn't really need a specific atmosphere like other materials. So even they are not trying with that, but the small fluctuation that will affect your flow in a larger manner. Okay, how do we compensate? We have temperature sensors at different level, or we can have a constant temperature sensor to the entire system that is going to give you input. But how do we have, like say for example there is a more heat built up because of delay, as we have there is a deceleration, even it is giving constant input, but as he said we are just modifying it, at the end it is going to give only lesser input. That time there may be possibility of accumulation of the material, or there may be possibilities of excess heat built up because of material is going to stagnate for a particular time period. How do we change, or how do we optimize it? Again, it has to given a like a loop system or a feedback system. We don't have any other option at all. We need to control the input pressure. Say for example there is a slight modification in the temperature, the input pressure can be modified based on that. We doesn't have any option at all. We can have like a internal loop, or we can connect it directly to the system itself. Again, the nozzle diameter, this is the one which is going to control the speed or a material ejection from the extruder head, right? How it's supposed to be. Generally we can have n number of nozzle shapes, you know very well. We can have like a conical or different ways. Say for example, what is the problem? Mostly for a particular product, this nozzle is going to be constant, right? For a particular build, say for example I'm going to build this entire mouse, for that this nozzle going to be constant. But we have an option in FDM, we can change the nozzles, interchangeable nozzles, that is possible here. What are the, say for example I have same nozzle throughout the build, what are all the problems? Or I may have interchangeable nozzles, what are all the problems? In which condition, same or interchangeable? In same there may be possibilities of clogging. Even you can have at the conical shape, at the ends there may be process of accumulation that may lead to clogging. So what we need to do, frequent change or maintenance of a nozzle should be done. Say for example, if we are, as we discuss even in other AM processes, if you are keep on stopping and changing it, that even leads to poor product development. That is a problem associated with even that. So how do we optimize? This is one of the problem associated with same that is constant nozzle throughout the process. How do we optimize is, we can maintain, prefer to have constant input itself, that maintaining the ideal temperature inside throughout the process, that will eliminate this error to the maximum condition. Got it? If I have interchangeable nozzles, I am changing it frequently after 10 minutes or 15 minutes, there may be a lead lag in the temperature variation in the product, that may even leads to poor product development. It may lead to even porous, those kind of errors. Even you can say the speed can be precisely controlled by changing the nozzle, that is possible. I may have, say for example there is a minor change in the nozzle exit part, like a small bigger mouth or smaller mouth, that even will change the speed of laying, as you know very well. Once it is done, that may lay up in a much faster way. So speed is directly controlled even with help of a nozzle diameter. So interchangeable in that sense, we need to have a proper look over, and then say for example for a particular product we may change 1 time or 2 times, that is ideal. And also if there is a possibility, we can maintain a temperature or a chamber pressure, or the entire unit should be in a constant temperature, that is better. Instead of having, like say for example I am removing a door and I am changing the nozzle, that time for sure this product will leads to some error, internal problems, or there may be distortion, or there may be dents present in the product development, that is possible. So material characteristics, and here the material characteristics also a major concern, because it is going to have a phase change within the system, not externally. Got it? Within the system, in that sense we need to know at least the basic parameters of how it is going to flow, what is the flow rate of the material when it is in a liquid state, and what are all the viscous effect based on that, creep effect based on that. How, say for example, I am giving a constant input, it is keep on laying it up. If there is a drop or a small clog in it, automatically this may affect the other process which is present inside. Can you understand? Say for example, there is a clog, material is going to be in that temperature for more time, what will happen? So likewise, we need to work with the material characteristics as well. If say for example the melting point of the temperature maybe 100 degrees Celsius or 200 degrees Celsius, in that sense it is keep on melting, or in that temperature itself the material is going to be idle for few minutes more than normal extrusion, then this may leads to internal change material characteristics, and there may be a entire change with the help of a characteristics which is not suitable for the product which is going to develop. There may be possibilities, and some cases they may evaporate and this may form a gaseous layer even. So that is like a worst scenarios, but mostly we are not going to have that much kind of temperature input that at that particular point, but there may be possibilities of material characteristics change. So we need to work upon that, and based on that, say for example the material can degrade at 200 degrees Celsius, we never ever go to that particular temperature with the system is going to work. Got it? So material characteristics you need to analyze previously before it is going to give a input or going to develop a product. Okay, this is again based on a gravity based system. Once it is converted into liquid, it is going to flow through it, right? That is how, say for example there is a huge temperature change, or there may be any other factor which is going to stop, like clogging or whatever it may be, that may leads to proper, that is the flow property can be modified based on that. Okay, so what we need to do, there shouldn't be any obstruction while it is flowing, because it's purely based on a gravity system, it's going to deliver out. So what are all the problem maybe based on that material is, the material is going to melt inside, this may give additional, or generally it has surface tension to it, particularly near the walls it is comparatively higher. So this surface tension also, if there is accumulation of the material, this may vary, or this may give additional stress to the material present inside, and this nozzle it is forcing outward, right? There may be a chances of internal dragging forces, or we can say like a reactive force based on this, because it is purging towards it, it's like almost forcing towards the nozzle. There may be a internal force developed through it, that we call it as like generally drag forces through the nozzle. That effect should be maintained. Mostly for all of these, the major is input. So once we have a proper temperature, say proper pressure input through it, we can eliminate most of these problems. So that's how we need to optimize always based on the input temperature, input pressure, that indirectly controls your temperature within the chamber. Again, say for example the material is laid up with a different surface areas. Say for example, consider a huge ball, it has very small thin surface area, it can have like a small surface area at the bottom, huge, that is more at the middle, and again thin at the top, right? This material have different cooling effect, right? This may leads to give a temperature to the surrounding maybe very little, say for example some 5 degrees or 10 degrees. This middle portion may give some 15 degrees or 20 degrees. This build up temperature to the surrounding may affect the system in some cases. So we need to work even based on that. Say for example larger structure, it may give additional heat delivering, and it may take more time even to get cooler. You can even play with many of your home based items, even you can test that. Say for example if you have bigger dosa entirely, right, it may take more time to get cooler. What we can do, we can just split it and keep it as a small pieces, it get easily cooler. So here it's a vice versa process. The smaller already we have very small at the bottom, this will leads to give only very minimum temperature, but this middle part is going to give maximum temperature. This temperature modifications along with the surrounding may affect the equipment which is present inside even, because it's a very closed, very compact atmosphere. We are not going to have a bigger versions, very smaller one, in that this may also affect. So how we can do, we can have the surrounding temperature which is going to be in optimized condition. There may be have some temperature sensors. Once it is higher than normal level, there may be some additional inputs. So for example, like a control valves, I can have additional temperature, I can set it out, or I can introduce some cool air to it, whatever may be, vice versa, or you can just let it out, that is also fine, because I don't want to change the entire temperature system until the product is going to complete. Okay, I don't want to keep on changing the temperature before building the product, because that is also played generally the atmospheric condition, you know very well, that is always have major concern in a product development. Even we can say a small temperature variation that may leads to have porous or dent or whatever, until say for example I have developed until a middle level, again this temperature is going to decrease. That time there may be possibilities of faster solidification, right? So that time the material have different properties. Can you understand the difference? So at least I can have a conducive or a closed atmosphere. This problem may be eliminated to a little level. Understand? These are all the major parameters, like optimization parameters concern. Once we are concentrating more on extruder unit and then the input unit, that is more than enough. That is more finite enough to get a optimized product developed. And now we are going to discuss about what is the future in FDM. Presently, you know, mostly they prefer to have a ABS kind of materials, wax kind of materials. What is the future? What maybe they can develop? As we were discussing, nano and composite materials can be built using the machines. Nano material you can see in SLA itself, right? You can see very micron level materials has been developed. You can see one example based on the 2-photon polymerization method. So similarly, they can go for a nano level of material development. What is the advantage is you can have better strength to it, and we can go for a better resolution of it, and the composite materials can be built using this. The entire composite material can be laid up. And what are all the major industry which we have now is, after the development of your electronic gadgets, the major industry is semiconductor industry. That semiconductor chips may be fabricated using FDM. That kind of possibilities are there, but at that moment there is no 100% developed product. Like as I said, these are all some of the research they are presently planning to develop the products. So you think over just we are making a semiconductor chip within even you know the chip size is very small, that is effective. We are laying it up within a short time period, we are increasing the productivity. Think about it. These are even you know very hard to lay up, and the small connections are really harder. You need very skilled person to develop the entire chip unit. So that's why they are planning to have using FDM kind of thing. But in FDM they may have, as we discussed, multiple material inputs. You know, the semiconductor chip has got different property and it has different material input, and internal layup may be using some other material. Even you can have soldering kind of inputs is required. So in those kind of areas you need to change the material. Even I can say 5 or 10 materials may be the input, but once it is done, this is some of the effective manufacturing method. Even if I have a plan of developing some kind of material based on working based on this, so even if you are interested, anyone can approach me even. So some kind of works still they are doing on it. And then the architectural models, much complex architectural models. You know, some of the bridges we cannot visualize the entire component. Even I can show another example which we cannot visualize as such, even with a 3D diagram. Even you can, they may have the entire component, along with that they may have the 3D design of it. It's harder for a designer or a developer to visualize it. In those kind of areas, this kind of complex architectural models is easy, because they can have a multiple split or you can assemble at the end. So we can easily visualize how complex it is. Even you can have a cut through view of it. That is, they are trying in this. And metal FDM, that you know very well, they are planning to have some kind of metallic strips or products which is going to give a input as a extruder component. So metallic inputs also there is a area to work with. One of the practical example which I have seen in real time, this is, you know, most of the aviation people, they have even interest in engines. That is the Kaveri engine. This is being developed for a long time. You know, the GTRE, gas turbine research establishment in Bangalore, the system has been developed a long back. The FDM system they have developed long back, but the problem with that one is they are unable to visualize the entire component for the engine. So for example, the entire engine may have 2000 product components or 2500 components, and you can have the fuel lines which is run across the engine. We may not predict where it is going, and in this kind of gas turbine engines, that is aero engines, there may be air tappings for different reasons. The air is being trapped and used for a internal air conditioning purpose, and even some parts of the engine itself, they will tap the air and they will cool it. So these kind of mechanisms are inbuilt. So think about n number of lines which is running around the engine. They generally mention it as LRUs, line replacement units. These units is really harder to visualize. Think about it, within this area you have n number of connections, say for example like 1000 or 500 lines are running across here and there. So they were worked a lot to isolate the part or isolate or identify the errors or whatever it may be. And even before developed, right, I have the full part, a component of engine. Even I can have the design, a 3D drawing of it, right. I can have like visualize from n number of directions, from top or bottom, whatever it may be. But still, what is the problem? I am visualizing at a one part only at that particular point. I don't know what is present inside it. Even in a cutaway view, I cannot visualize in 3D as I have a component. Can you understand the difference? Mostly, if the component is complex, they need to go for a proto development, right, or a scale model we call it, that we need to develop. That is mostly we are forced to do even. So think about the conventional fabrication cost for developing a normal proto like this. What is the cost? $60,000. And what is the time period? 12 months. This is I didn't take this data from like unauthenticated. This is from a journal. So you can see the journal reference as well here. So think about the change, but using this FDM method they have developed with 20,000 and within 1.5 months. That is more required at the moment, because even there is the same cost, but there is a marginal reduction in a time period. So that is how where you can think about it. That's why I mentioned that silicon chip as well, because that is really you can say like a jewelry component. It's very costlier. In that case, if you are maintaining or reducing the time period and you are giving 100% accuracy of the product, even if it is costlier than the normal manufacturing, they are ready to adopt this method. Because you can say, if there is after a development a person do a small mistake in it, for sure there may be a damage of the entire component. Even the skilled person missed at a particular point, that may lead to huge variation in it. Likewise, if they work on it, even the material become little costlier than the normal product developed, they prefer this method. So likewise, you can work on which are all the areas. You can think about one of the areas like this, and you can see this is one of the freehand extruded. Say mostly our people, they prefer to draw easily. So for that they have developed the 3D doodler. They have developed a pen like this. The input they have given like a normal filament. You can draw freely and you can develop a component. So this is much easier, much easier I can say, because most of us, we have a skill of drawing using a pencil instead of using a computer, because now the people are in that level of directly using the computers to start up with. But particularly in our age, mostly we use freehand drawing. That is the base idea. They developed this system. You see the entire component he has designed with a normal, like a normal sketch. You can extrude the head. You can see here, this is the extruder head. The filament is here. You can see the red one and the black one is here. So likewise, the blue one also is here. It's not visible actually. So we can just extrude and you can develop an entire component. So this is one of our easiest way. Can you understand how the system is working, particularly based on FEM? Because day by day the system is getting sophisticated and become easier, even easy to adapt, but the system internally is become more and more complex. That is there, but it's the easiest way to adapt. Only the extruder system, you can have it in your hand, you can develop whatever product it may be. They developed a number of products, not alone specifically this kind of things. Like they have developed even like solid objects with assembly manner. Say for example, they develop a Eiffel Tower, for example. They develop with a different fixtures, like different pieces of it, and they will assemble at the final. You can get the 3D model of it. You understand? In this session, we have discussed about process optimization for fused deposition modeling in future and in real-time applications, and the freehand extruder.
Sir, in terms of electronics manufacturing, how much FDM can foray into it, and if we are seeing the process parameter, the nozzle diameter, how much small it can be and how much it is achievable?
Obviously, we saw we can change the nozzle diameter at any time. That is possible here in the system. Say for example, the product size, the entire component size may be hardly less than a centimeter. So for that, even the nozzle size may be, we can have like a small needle, even in terms of microns. That is possible because we achieve a little bit in terms of photopolymerization process. You can see the micron structures has been built using photopolymer, but the input there is laser. We cannot say 100% accuracy that is possible in this kind of nozzle extrusion method, but there may be possibilities to have a very minimum size of nozzle. As we are keep reducing the nozzle size, there may be a lot of internal drags is possible. So we need to overcome that.
Sir, what is the important bottleneck that is preventing FDM being the next big thing in additive manufacturing?
As far as my knowledge concerned, FDM is one of the key areas. As I said, we can have it as a home built one. The major concern or a major bottleneck to that one, to my concern, is the product developed costs can be reduced little bit. So that's why they are working on materials more, because that will leads to, as Sir said on that day, to develop a bottle, no one is ready to afford 5,000 rupees or 6,000 rupees. That is a harder one. So if I have a material in such a way that the cheaper material, that may leads to, that's what always we need to think in AM. For a small volume, the component should be expensive. Those kind of components are much ideal to develop using this.
Regarding material, Teflon has very good physical properties. Have you ever tried in Teflon in FDM?
I didn't try, but even I think Teflon they didn't try at the moment, as far as my knowledge concerned, because like you have, even as I said, even they tried with ceramic powders, but Teflon, as far as my concern, I think they didn't try at the moment. But as you said, you can rebuild, the system can be rebuilt as you need. That is the advantage. Once that is a major advantage in FDM developed compared to other AM process. They think the equipment is costlier or material is costlier, whatever it may be. The normal man can have a clear visualization of AM very easily after development of FDM. Even as I shown in the last session, you can see the pattern has been increased a lot after they have a clear idea how the component is being built. That is a reason, major reason. And another reason that AM has got that much familiarity. Even they tried even in 1950s or 40s, but they didn't achieve it as a component which is visualized. So that is a concern. There was much developed in it. After the FDM kind of things they have developed with a cheaper rate, the people has got vision. They can easily build up. So they are remodifying and restructuring based on their needs. Now the industry is booming based on this.
Sir, what is the maximum axis that the nozzle can move?
Maximum axis
movement.
You mean
X and Y? It is possible for Z or?
That's what, as I said on previous session, if you use, say for example, now I can say only 10-inch cast 10-inch, X10 and Y10, but if we have flexibility like what they are using in civil, that is a construction industry, they are laying up the entire house. If we have any free from transmission, something like that, or as we seen like a free from extruder, we can go for a number of distance. Even there is a DST project in India. I think some Welltech is doing that. They are working on particular robo assisted FDM or any other AM process, I think so. What they are doing, they are giving some robo arm which is free to move.
So my question is, the selection of nozzle is based on material or on the finished products?
Again, this is a what to say, the principle is like a crisscross. Say for example, I have the nozzle size based on the components is going to develop. That is easiest way to optimize even. But in some cases, the material property is varying based on the component which I am developing. Say for example, inbuilt temperature or whatever may be the case, that time prefer to go based on the material. So preferably you don't want to make such a complex idea based on this. Better go on the input pressure, that is fine. Nozzle size defining based on the input pressure so that it is going to liquefy and it is going to come up. You can focus in such a way. Because it's like again optimization parameter has to be based on these two. You need to have even interchangeable nozzle at the moment, or you can have you heard about the variable nozzles? Variable nozzle, that is the size can be altered even during when it is in operation. That is also possible. Even you can have small shutters. Again, the system is going to become more and more complex. That's what if you want to optimize, there is option like this, like a variable nozzle you can go. Change the nozzle shapes as far as we need it. Say for example, at a particular layer, like I need have a thinner or a speed maybe more. At that level, I can just reduce the nozzle level. May even like a shutters I can use, or I can use the conical shapes I can tilt. That is possible. That again, the system become more and more complex. So that is a major concern. Again, the equipment cost will go higher. Maybe my end product may not be that much costlier for me.
So please elaborate on variable nozzle concept that you said about how the various actuating mechanisms inside the material involved.
Say for example, I have a conical shaped nozzle, right? I can have a shutters at the tip. I can just close like this or open. Only imagine the internal part of it. Just you can move shutters like this so that the flow is very less. Or this conical part itself, I have an external say for example like actuators or some small hydraulic input like in the corner. I can just move this conical shape itself so that once it is moved throughout the area, it is going to stretch like this. Like I am imagine like a external input I am giving, not an internal input. Externally for the nozzle, I am just like imagine like a hydraulic actuator is going to stretch like this. It can be connected circular wise, it can be moved in this way. That is possible.
The material used, you know?
Sorry.
Can you please tell me the material used and the actuating mechanism?
Actuating mechanism, hydraulic is possible. That's what the problem is. For a small level, you do not hydraulic, pneumatic or something like that. Even like a mechanical inputs. Say for example, something is pushing like this, which is going to stretch like this. That is enough to move it. Small shutters also you can use like a normal knob kind of structure. Once there is some mechanism which is going to turn like this, which is going to close or open or something like that. That is possible. You don't have to go for imagine like a bigger actuators, like hydraulic actuators or pneumatic actuators. Even mechanical screws will do. That is possible. But these are all like it is not existing at the moment, which I am thinking and I can just incorporating what are the possibilities of it. So don't ask me 100% how this can be achieved. Even I don't have the solution for that, but I am trying to manipulate the systems which is already present and how to achieve that one.